Welcome to the Explainer. Okay, let's just dive right into this. Today, we're exploring the invisible, kind of fascinating world of chemicals that are literally all around us, every single day. I mean, from the food on our plates to those heavy-duty substances scientists use in research, we're going to zero in on acids, alkalis, and those absolutely crucial lab safety rules that keep us from, well, getting hurt when we handle them. Here's the roadmap for today. 1. Acids and alkalis around us. 2. The danger of strong chemicals. 3. Essential lab safety rules. And 4. Decoding hazard warning symbols. All right, part 1, acids and alkalis around us. Everyday chemistry. Because honestly, to really wrap our heads around these concepts, we just need to start right in your own kitchen. So, if you've ever bitten straight into a lemon or a lime, you already know that completely unmistakable, sharp, super tangy taste. That zing, it's actually from something called citric acid. Now, because it's totally safe for us to eat and digest, citric acid is categorized as a weak acid. It's just a great everyday example of how we interact with chemical properties all the time, completely without realizing it. Now, what's really interesting is when we contrast these weak everyday acids with their counterparts, everyday alkalis. While acids give us that sour punch in fruits or fizzy drinks, alkalis are a whole different ballgame. You'll find them a lot in common cleaning products. They contain stuff like sodium hydroxide. And here's a weird fact. If you actually got a weak alkali on your skin, it would feel distinctly slippery or even soapy. It's a completely different physical sensation. In fact, they are so different, they're literal chemical opposites. If you were to mix an acid and an alkali together, they react by essentially canceling each other out. And whether a substance is acidic or alkaline isn't just some random quirk. It's a fundamental chemical property that dictates exactly how it behaves in the real world. Which brings us to part 2, the danger of strong chemicals. High-stakes lab hazards. We're stepping away from the kitchen counter now and heading into the extreme environment of a chemistry lab. Because in the lab, we are definitely not just dealing with lemon juice anymore. We're handling strong chemicals that carry severe, life-altering risks. Take the word corrosive. By definition, a corrosive chemical is a highly dangerous substance that can literally destroy living tissue and cause severe chemical burns. I really want to emphasize this. If a strong acid or alkali gets on your skin or in your eyes, it basically dissolves the tissue. It is incredibly dangerous. And this brilliantly illustrates the stark contrast between these environments. In one, you've got harmless, heavily diluted stuff, vinegar, fruit juice, your standard mild surface spray. But step into the lab, and boom, you are dealing with concentrated, hazardous chemicals locked in sturdy bottles with some very intimidating warning labels. It's the exact same fundamental chemistry, but the concentration level, that completely changes the threat. Let's walk through some specific names you'll run into. First, the heavy hitters of the acid world, hydrochloric acid, sulfuric acid, and nitric acid. But seriously, do not underestimate the other side. Strong alkalis are just as dangerous and corrosive. Things like sodium hydroxide, potassium hydroxide, and calcium hydroxide. Never, ever make the mistake of thinking alkalis are safe just because you find weak versions in your home cleaning supplies. In their concentrated lab forms, they will cause massive chemical burns, just like the acids do. And because these substances are so unforgiving, we move to part 3, essential lab safety rules. Handling with care. These are the absolute non-negotiable procedures for staying safe. I want to walk you through these steps because honestly, there's a rock-solid scientific reason behind every single one. Number 1, always stand up to work. Why? Well, if you spill something highly corrosive, it's going to fall straight down to the floor rather than pooling right in your lap. Number 2, wear safety glasses. Your eyes are incredibly vulnerable, and frankly, nothing should get in them, ever. Number 3, when you take a lid off a bottle, place it upside down on the bench. That stops any corrosive residue on the lid from burning the table, and it stops dirt on the table from contaminating your pure acid. And 4, replace those tops immediately. It prevents spills and stops you from accidentally putting the wrong lid on the wrong chemical. So, the crucial point to remember for first aid is this. If you spill an acid, wash the area with a lot of water. The water dilutes the acid. If an accident happens, dilution is your absolute immediate line of defense. Both alkalis and acids can be diluted with water, which just lowers their concentration and buys you time, making them less immediately destructive to your skin while you get help. Actually, let me clarify a really important nuance here. Just because an acid or an alkali has been diluted with water doesn't mean it's suddenly totally harmless. Even diluted, these chemicals act as irritants. They're still harmful, and they can absolutely still irritate your skin and eyes. And that right there is exactly why hazard warning labels are absolutely mandatory, even for the weaker solutions. Which cues up our final segment perfectly. Part 4, decoding hazard warning symbols, reading danger signs. These red diamond labels are basically a global visual vocabulary scientists use to communicate extreme danger instantly. Let's decode this first batch. That exploding icon? Pretty straightforward. It means explosive. This is a substance that can quite literally blow up if it hits a flame or gets too hot. Next is the flame icon, which means flammable, warning you that the chemical catches fire super easily. And then there's the oxidizing symbol. It looks like a flame burning over a circle. That indicates a substance that releases a massive amount of heat the second it comes into contact with other chemicals. Let's keep going and see how this builds. That icon showing chemicals burning right through a material and a hand, that's corrosive. Like we talked about, it destroys living tissue. Then you have the classic skull and crossbones. That means toxic, clearly signaling that the substance is intensely poisonous. And that striking dead tree and fish symbol, that indicates the chemical is hazardous to the environment, a stark warning of the severe damage it could do to nature if it ever escaped the lab. Finally, let's distinguish between these last two. The large exclamation mark just denotes a general health hazard, meaning it can cause harm, like intensely irritating your skin or eyes. But look at the silhouette of a person with the internal damage graphic. That is the serious health hazard symbol. It warns of severe, long-term internal health problems. Honestly, whenever you're in a lab, these symbols are your absolute best friends. They tell you exactly what kind of invisible threat is hiding in that bottle before you even unscrew the cap. So, as we wrap up this explainer, I want to leave you with something to bridge the gap between that high-tech lab and your own living space. Take a look under your kitchen sink tonight. Seriously. Think about which of these extreme hazard warning symbols actually belong on the chemical cleaning products hidden right there in your home. You might just be shocked at how much intense chemistry is sitting quietly in your cupboards. Thanks so much for exploring the science of acids and alkalis with me today. And hey, stay curious out there.